Hi everybody, Justin here from chemistrynotes.com, and today we're continuing with section 16, spontaneity, entropy, and free energy. So this is video number 3 from section 16, and in the first two videos we talked primarily about entropy, S, or the change in entropy, delta S. And entropy is the measure of the amount of disorder or randomness in a process or chemical reaction. And delta S we will use today because it is a part of this new idea, Gibbs free energy G, or more commonly delta G, the change in free energy. So video number 3 kind of gets to the crux of what I want to talk about and focus on in section 16, which is the free energy change delta G and how you can look at the value of delta G to determine if a reaction is spontaneous or not. So Gibbs free energy G, at the top of our first page of notes here, Gibbs free energy is defined as a thermodynamic function that not only is related to spontaneity, but also deals with the temperature dependence of spontaneity. This is the most important equation for determining if a process is spontaneous or not. Why? Well, because it concerns itself with delta S, the change in entropy, concerns itself with T, temperature, and also the change in enthalpy that we learned all about way back in section 6. All right, so delta G is equal to delta H minus T delta S. And if delta G is less than 0, in other words, if delta G is a negative number, a negative value, then our process is spontaneous. If delta G is positive, if it's greater than 0, then the process is not spontaneous, but instead, if there's a reverse process, that is spontaneous. And of course, these are held at constant temperature, constant pressure. Now, to calculate delta G, in other words, to calculate the change in free energy, you have to compare and consider the delta H and the delta S terms. So if you go up and you look at the boxed equation, right, you have delta G equals delta H minus T delta S. We want delta G to be negative if the process is going to be spontaneous, if the process or reaction occurs naturally in the forward direction all on its own without any outside influence. So we have to take into account delta H and its magnitude, delta S and its magnitude, and also the fact that temperature is in that equation. All right? So let's do an example. At what temperatures is the following process spontaneous? And usually when I write the word process, I'm referring to a chemical reaction, at least in terms of this section, section 16. At what temperatures is the following process spontaneous at 1 atm pressure? We have Br2 liquid going to Br2 gas. So we certainly are aware of why the delta S value is positive. We're going from a liquid to a gas, right? So it should be no wonder that delta S is a positive 93. It's joules per Kelvin per mole. And then notice delta H is in kilojoules, 31 kilojoules per mole. So this is an endothermic reaction. And then it says, second question, also, what's the normal boiling point of Br2 liquid? Normal boiling point, by the way, is the boiling point of a substance at 1 atm pressure, which is what we're at. So how do we approach this problem? Well, here's our solution. Delta G must be negative in order for this process to be spontaneous, right? So in the equation, delta G equals delta H minus T delta S. We want to just be barely below 0 for delta G. Anything negative means we're spontaneous. So I can actually find the threshold temperature if I set delta G equal to 0 and then solve for that particular temperature. Here's what I mean. If I set delta G equal to 0, right? Remember that little degree sign means we're at 25 degrees Celsius, so and 1 atm. So delta G equals 0 equals delta H minus T delta S. T delta S equals delta H. T therefore is delta H over delta S. Make sure I have everybody in kilojoules, or as I've done it, everybody in joules. And we find out that the temperature, the threshold temperature, is 33 degrees Kelvin. All right? 333 degrees Kelvin, sorry. So the temperature should be above 333 degrees Kelvin. If that's the case, and the temperature is above 333 degrees Kelvin, in other words, above the threshold temperature, well then the forward reaction is spontaneous because the second term in delta G equals delta H minus T delta S, in other words, the T delta S term is larger and more significant, therefore we're going to get negative values. Okay. So again, that should not have been 33 Kelvin, that was 333 Kelvin. So when the temperature is equal to 333 Kelvin, spot on 333 Kelvin, the free energy change, delta G, is going to be equal to 0. Okay? And the liquid and solid bromines, the liquid and gas phases are going to be in equilibrium with each other. So they're coexisting. Okay? When temperature equals 333 Kelvin, the free energy change, delta G, equals 0, and the liquid and gas phases of Br2 coexist at 1 atm. Well, that's what boiling point is, right? When the liquid and gas phases are coexisting. So the normal boiling point, because we're at 1 atm pressure, is 333 Kelvin. All right, next topic. Free energy, G, and chemical reactions. Right? We've already seen a little bit of this. We've seen one way to calculate delta G, right? One way to calculate delta G is delta G equals delta H minus T delta S. That was the first equation I boxed up on page 1 of our notes. So the standard free energy change, delta G with a little degree sign, right? The standard free energy change, delta G, is the change in free energy that occurs when the reactants in their standard states are converted to products in their standard states. So let me read that at full speed now. The standard free energy change, delta G, is the change in free energy that occurs when the reactants in their standard states are converted to products in their standard states. All right? Knowing delta G is useful because, first of all, it tells us if a reaction is spontaneous or not. If we know the delta G for a reaction and it's negative, well, then this reaction goes in the forward direction. No problem. It happens naturally, all on its own, without any outside interference. Okay? So knowing delta G is useful because the more negative its value is, the more likely it is that a reaction will occur in the forward direction. In other words, shift right. Okay? So I've already mentioned that there's one way so far that we've learned to calculate delta G. There's actually 3 ways to calculate delta G. If you remember way back in section 6 when we talked about delta H, enthalpy of reaction, right? The heat of a reaction. There were 3 ways to calculate delta H. Well, there's also 3 ways to calculate delta G. Number 1 we've already seen. So let me just kind of recap what number 1 was. Number 1 says, using the equation delta G equals delta H minus T delta S at constant temperature and pressure. And we saw that on pages 1 and 2 of this video. And then number 2 and number 3 we haven't done yet, but we're going to explore them right now. So the second way to calculate delta G is using procedures similar to Hess's law back in section 6 when we calculated delta H. That's when they give you an equation that you're trying to make, and then they give you like maybe 2 or 3 or even 4 different equations that you need to use in order to make the equation you want. And you add up all the individual delta H's. Same thing here, but you add up all the individual delta G's. So, example, from the data provided below, calculate delta G for this reaction. This is the reaction we want to calculate delta G for. has a box around it. It is 2 moles of CO plus 1 mole of O2 yields 2 moles of CO2 gas. Now, I'm going to show you a series of equations here, and we need to use these equations in order to make the equation we see in the box. So, data. We have a first equation, 2CH4 plus 3O2 yields 2CO plus 4H2O. Delta G for that particular reaction is minus 1088 kilojoules. Second equation, CH4 plus 2O2 yields CO2 plus 2H2O. Delta G for that reaction is minus 801 kilojoules. So these are the only two reactions they've given us. We're going to use both of them and either flip them or maybe multiply one through by a coefficient, or flip one and multiply it by a coefficient. We have to work with it in order to make what we see in the box. So the solution, there's more than one way to approach these, but for me, I noticed that the only way to get 2 moles of CO was a certain way, right? So here's what I'm going to do. The top of the next page of notes here, we have 2 moles of CO plus 4 moles of H2O yields 2 moles of CH4 gas plus 3 moles of O2. Okay, so delta G for this plus 1088 kilojoules. All I did was take the first equation in the data and flip it. All right. Now the second equation I'm writing here, and I always like to line up my reaction arrows so I can just kind of summarize what's the reactants total and what's the products total underneath all this. But the second equation is 2CH4 plus 4O2 yields 2CO2 plus 4H2O, delta G, twice minus 801 kilojoules because I multiplied that second equation through by 2. Okay, cancel like terms, summarize what's left, and sure enough, I end up with 2CO gas plus O2 gas yields 2CO2 gas. That box right there is the same as the box on the halfway through the last page. So delta G, add those delta G's up, plus 1088 plus 2 times the negative 801 kilojoules gives me a delta G value of minus 514 kilojoules. So the reaction in the box is spontaneous in the forward direction. All right, that's the second way that we can calculate delta G. Third way is using standard free energies of formation, delta GF. Okay, we have done this process twice before. Once way back in section 6 when we did heats of formation and delta HF. And then we just, in the last few videos that you've seen for section 16, we were able to do that with the value for delta S. We can calculate delta S this way too. So standard free energies of formation, change in free energy that accompanies the formation of 1 mole of substance from its elements with all of the reactants and products in their standard states. That's why we have the little degree sign. Now it says formation of 1 mole of a substance from its elements. So if I'm given a substance that's already in its elemental form, then just like delta H back in section 6, the delta G formation is going to be 0. And it says that right here in our second bullet point. Delta GF equals 0 for elements that are already in their standard states or already in their elemental form. So here is the funky looking equation that I don't like to use. I'll give you my own version on the next page. But basically it's saying delta G is equal to the sum of the free energy of all the products minus the sum of the free energy of all the reactants, taking into account the coefficient or the number of moles of each reactant or product. Now the way I like to write it is similar to the way we wrote it for delta S in the last video. Delta G is equal to the sum of all the free energies of formation of products minus the sum of all the free energy of formation values of reactants. Okay, so sum of all GF values of products minus the sum of all the GF values of reactants. Products minus reactants. But, and I've got a little arrow here, don't forget to consider the number of moles of each reactant and each product. All right, let's do an example using this third way of calculating delta G. the free energy change. Example, is the following reaction spontaneous under standard conditions? Standard conditions, remember, we have a little degree sign, so standard conditions, it's 1 atm pressure, 25 degrees Celsius. So here's the reaction. C2H4 gas plus H2O liquid yields C2H5OH liquid. The states of the reactants matter. So I have to look up C2H4 gas, H2O liquid, and C2H5OH liquid in a table or at the back of your textbook. Sometimes it's referred to as an appendix in the back of your textbook. Same appendix or same table that has all the columns for heats of formation. And this is free energies of formation that I'm concerned with now. It also had the entropies as well. So the 68, the negative 237, and the negative 175, these are all values that I looked up in the table in the back of my textbook. So delta G is products minus reactants. So it's the minus 175 minus the sum of all the reactant GF values. Negative 237 plus 68. Everybody here had a coefficient of 1 in front of it, so it worked out kind of nicely, and the answer is minus 6 kilojoules. Those little circles, 68, minus 237, and minus 175, these are in kilojoules per mole. All right? Now, we have one more video left in section 16. Section 16 is our shortest section. In other words, it's our shortest chapter. So chapter 16, section 16, same thing. This is our shortest section. And the next video, video number 4, is our last one. So let's go see that video right now. We can get section 16 all finished. All right, stay tuned for the next video.